Nice day, nice mountain, a peaceful national park in the northwestern USA. But will it stay that way? Watch this. A volcanic eruption. But what caused it? What's happening in a volcano? This is most people's image of a volcano. Obviously the transfer of a huge amount of energy. Certainly spectacular. Fountains of lava erupting from a mountain and flowing down its slopes. But what is lava? Take a look as it cools. New rock, thousands of tons of it. Follow the lava flow down the mountain and eventually it all cools. New rock, new land. But there isn't only rock here. Gases dissolved in the hot lava escape as it reaches the surface, carbon dioxide and water vapour. But it's all a matter of energy transfer. Energy is being transferred from below to the surface of the Earth as heat. And not only in volcanoes on land. These remarkable pictures show that lava flows occur underwater as well. Again, energy is transferred, but underwater lava cools much more rapidly. Energy is transferred to the water as heat. The rock in contact with the water cools so rapidly that it fractures. More molten lava streams out and the process repeats itself. But this rapid cooling has an effect on the solid rock formed. The crystals within the rock are much smaller. It has a finer texture than volcanic rock on the surface. We tend to think of volcanoes as being mountains, but there are probably more submarine volcanoes than ones on land. But what kind of temperatures do you need to melt rock? Different rocks are composed of different minerals, so there's a range of melting points, 2,200 to 2,800 degrees Celsius. Take a sample from the hot lava near the point where it meets the surface, and it's at a temperature of about 3,000 degrees Celsius. And it doesn't transfer its energy to the surroundings rapidly. Even after flowing on the surface for up to 5 kilometers, it's still molten. Certainly bad news for anything in its path. Stopping flowing lava is no easy task. It's all a question of transferring energy to the surroundings. Even when lava meets the sea, it continues to flow. But what's the source of this enormous amount of energy? We know that lava comes from beneath the surface of the Earth, but how far down? How hot is the Earth beneath our feet? Well, we can measure it. Travel down a deep mine shaft. At first, it's cooler than the surface above. The sun's radiation doesn't penetrate this deep, but go down further and the temperature rises. It gets hotter, but nowhere near enough to melt rock. So how far down do we have to go to meet molten rock? Let's try the world's deepest hole, 12 kilometers deep in the Kola Peninsula in Russia. The temperature continues to rise. At the bottom, it's 49 degrees Celsius. But at that rate of increase, how far down would you have to go before the rocks melt? How can we test our hypothesis that there's molten rock below the surface? This is an earthquake, another massive energy transfer. But let's try to measure it. Here's the readout from an instrument which measures earthquake vibrations, a seismograph. But look at the pattern. It has 3 sections, 3 different waves arriving one after the other. The third set of waves are simple. Drop an object into a liquid and energy is transferred as waves, which spread out across the surface. Same in an earthquake. Surface waves spreading out from the focus. But there are other waves produced, waves that travel through the liquid. You can't see these pressure waves, but they travel like sound waves, as alternate compressions and expansions in the water. But what happens if you change the liquid? Take a denser liquid, like tar. Denser liquid, faster waves. But switch that around. If we can measure the velocity of the waves, we can calculate the density of the material through which they are travelling. But the Earth's not a liquid. Pressure waves travel even faster through a solid like rock. The denser the solid, the faster they travel. So that's 2 kinds of waves taken care of. But pressure waves aren't the only way of transferring energy through a solid. There's yet another type of wave. They're easier to see in a less rigid material, like a jelly. Watch the sides of the jelly. Hit it and they ripple. The particles in the jelly move horizontally, but the waves travel up and down. It's like shaking a rope. The rope oscillates from side to side, but the wave travels up and down. These are called transverse waves. But transverse waves can only be transmitted by a rigid material. They cannot travel through a liquid. But just like pressure waves, the denser the material, the higher the velocity. Back to the earthquake. Now it's a bit clearer. Different parts of the seismic trace caused by different types of wave. First to arrive, those with the highest velocity, the pressure waves. Then the transverse waves, which also travel through the Earth. Finally, the slower but larger vibrations which travel across the surface. But how can we use these waves to find out what lies beneath our feet? Say there's an earthquake at the North Pole. Seismic waves will spread out from that point and can be detected all around the world. But the waves travelling across the surface won't tell us much that we don't already know. Better concentrate on the waves that travel through the Earth. Pressure and transverse waves also spread out from the source of the earthquake, but they travel through the Earth before reaching the surface where they can be detected. But pressure waves have a higher velocity, so they arrive at any detection site first. But thinking about two sets of waves is complicated. Let's just consider the transverse waves. What would happen if the Earth was solid rock, just like the rock we see at the surface? We know the velocity of transverse waves through rock, so we can work it out. As you'd expect, the further you are away from the earthquake, the longer the waves take to arrive. But here are the actual results. Not what you'd expect. Close to the source of the earthquake, the waves arrive earlier than expected. That means they must be travelling at a higher velocity. But what does that tell us? Faster waves, denser material. So the rocks deep within the Earth have a higher density than the rocks on the surface. But that's not all we find. Suddenly, the waves stop. Above a certain distance from the earthquake, and transverse waves can no longer be detected. But what could stop them? A liquid. Somewhere in the centre of the Earth, there's a liquid. Put all this information together and we arrive at a model of the Earth's structure. On the outside, the kind of rocks we can see, the crust, but in fact it's only a thin skin. Below it is the mantle, solid, but the rocks are much denser than the crust. In the centre of the Earth, a liquid core, but under the tremendous pressure of the thousands of kilometres of material above it. But if the crust is solid, and so is the mantle beneath it, what produces lava? Lava is a liquid, we can see that. But where does it come from? The crust is solid, and now we know that so is the mantle beneath it, but the mantle is also very hot. What could prevent a hot solid from melting? Pressure. Take a pressure cooker. By sealing the lid, the water can be heated above its boiling point. The vessel is sealed, the pressure inside increases, the water doesn't boil. Same principle in the mantle. No lid this time, but huge pressures produced by hundreds of kilometres of overlying rocks. But this still doesn't tell us where lava comes from. Or does it? Release the pressure, and the water in the pressure cooker boils. Same with lava. Release the pressure above the mantle, and the hot mantle rocks melt and flow upwards. In some places there is a steady release of pressure. Steady release of pressure, steady melting and upward movement of molten rock. Result? Volcanoes like these in Hawaii, predictable enough to approach. But not all volcanoes are so predictable. Why the violent explosion? Take a fizzy drink. Watch what happens when the pressure is released suddenly. Same with explosive eruptions like Mount St. Helens. Before the eruption, the mountain swelled up. Then something gave way. All the gases dissolved in the lava were released by the sudden release of pressure. The top of the mountain was literally blown off. Energy transfer on a huge scale. But does it take place all over the world? These are volcanoes. And these are earthquakes. Earthquakes and volcanoes are both sites where energy is transferred. But why do these energy transfers only happen in some places and not others? Energy is transferred as heat from the Earth's core through the mantle to the surface. Some of this energy is transferred through volcanic eruptions. The same process of energy transfer is happening on a smaller scale in this lava lake on a volcano in Hawaii. But can it tell us something about the processes going on inside the Earth? What happens when hot lava reaches the surface? It cools and forms a solid crust over most of the lake. But hot lava is continually rising to the surface below the thin crust, transferring energy as heat and melting the solid rock. The crust is continually destroyed and reformed. But this doesn't happen all over the lake. Hot lava emerges in some places, and the cooler, solid rock of the crust is broken up and descends beneath the surface in others. The energy transfer happens only in some places. Take a look at this lake from above, and you can see a pattern. The crust is divided into a series of plates. The transfer of energy happens mainly at the junctions between them. Remind you of anything? Localized energy transfer again. Volcanoes and earthquakes. But does that mean there are plates on the surface of the Earth? Maybe there are. Look at Africa and South America. Notice anything about them? Their outlines are surprisingly similar. Looks like they could once have been joined together. But now there's an ocean between them. How did they move apart? Here's a clue. There's a line of underwater volcanoes down the middle of the Atlantic. Molten rock wells up at these volcanoes, pushing the continents apart, and it's still going on. You can see the same process at work in the lava lake. Hot lava rises between two solid plates, pushing them apart. Just one difference. Under the huge pressures of the mantle, the hot rocks are solid. They do flow, but very, very slowly. A bit like glass. But hang on a minute, these underwater volcanoes are producing new crust. But the Earth's crust can't be growing everywhere. Back to the lava lake. Where two moving plates meet, they slide beneath each other, and the solid crust is pushed downwards. This happens at the edge of some oceans. As the spreading crust under the sea meets a continental plate, it dives under it into the mantle. But how does that produce volcanoes on land? The descending rocks become hotter and melt. Wherever the pressure above is released, volcano. It's all a question of the transfer of energy as heat. Stand next to a volcano and the transfer of energy is obviously very rapid. But the same processes causing these violent fountains of volcanic lava also produce the unbelievably slow movements of continents. We tend to think of the Earth's surface as unchanging, but it's all a matter of timescale. This is how the world looked 200 million years ago. All the continental plates were joined. Since then, they've been moving around about as fast as your fingernails grow, all due to the transfer of energy from the interior of the Earth. Energy transfer can literally move mountains, and oceans, and rivers. And if it all seems impossibly slow, that doesn't mean it's not impressive in close-up.